Hello and welcome to another lecture of Introduction to Astrophysical Fluids. So in this lecture we continue our discussion on the effect of rotation in astrophysics. Now, in the whole discussion, in the whole series of discussion on the rotational effects in the framework of astrophysics, we started by saying that how the effect of rotation can be included in the equation of dynamics of a fluid, and then we also said that the treatment can be very much simple if we just place the observer to a co-rotating frame of reference with respect to the rotating fluid, and if the fluid is actually moving with moving with a solid body rotation, that means a constant angular speed, then we can if we just place this in the we just place the observer in a co-rotating frame, then the fluid is everywhere at rest with respect to the observer. So with respect to the observer, then the treatment, the whole equation becomes just a problem of hydrostatics, but of course there will be some centrifugal term with respect to the normal hydrostatic problem. Okay, and if it is not like if the fluid is not really rotating in a solid body rotation, then it will rotate, of course, with different angular velocities. That is called the differential rotation, and for that we cannot make the velocity, fluid velocity at every point to be zero, but still the problem becomes much more simpler. Then we studied some interesting consequences of this rotation. We said that the Kelvin vorticity theorem is modified now, and you don't need an initial vorticity to generate the vorticity in the vorticity in a rotating fluid. The rotation itself actually will create the vorticity. Okay, so this type of thing we already saw, and then we discussed a very interesting theorem called the Taylor-Proudman theorem, and finally we discussed in the last lecture the effect of rotation on self-gravitating mass, which is of enormous practical interest for the astrophysical bodies. Okay, mostly the stars. Okay, now in this, and also we explored then two possible cases. One is the spheroidal type of solution, and one is the ellipsoid type of solution. Okay, so and of course these all are laid, so these two possible solutions are laid from our experience of observational experience. Okay, what we in general see in nature. Now it is also true that for the simplicity of the analytics, okay, we assumed a very special type of fluid, which is the incompressible fluid, and we also said the fluid is rotating with a solid body rotation. Okay, if the fluid is no longer incompressible, fairly compressible, and if the fluid is not rotating with a solid body rotation, then what happens? Then, in some cases we still can conclude something very much interesting. That is exactly what we are going to discuss in this lecture, but not very rigorously. Okay, so sometimes some analytical treatments can be done for special cases, but for a general compressible fluid and general differential rotation problem, solving the effect of rotation on a self-gravitating mass is enormously complicated. So one very smart way is to simulate them numerically. Okay, and this is also a subject of active research. So if you are interested, you can see over internet different papers, both old and recent papers, and you can be updated about the ongoings of the research, okay, corresponding to this subject. Now here in this lecture, we will simply try to do some qualitative discussion, but somehow doing some small analytical things. We will try to like explore some qualitative conclusion, okay, or qualitative extract some qualitative information about the importance of rotation in different stellar objects. Okay, so as I just said that analytically what we presented, I mean till now, is only for compressible fluids and solid body rotation. But we know that most of the stars are made of compressible gas, okay, and that undergo differential rotation as well. For example, the sun is a very good example where the star is not going as not undergoing a steady, I mean solid body rotation. Actually, we discussed about this, that only for the slowly rotating stars the establishment of a solid body rotation type of regime can be possible. For a star which is rotating with moderate or fast, I mean moderate or large angular speeds, okay, then the possibility of differential rotation cannot be avoided. Then the analysis is extremely complex, okay. But as I just said, that the only resort is to do some numerical simulations, and of course for some special cases you can still do some analytical treatments. Now in this lecture we will just discuss some qualitative things, okay, but these qualitative things will be discussed in the light of some simple, very small 1 or 2 liner analysis, including the compressibility and the differential rotation. Maybe the differential rotation will not be included in this lecture, to be very honest, but only we will take the compressibility into account, okay. So if you remember, first we consider the case of a compressible star with solid body rotation, okay. Now if you remember the balance equation, okay, from the basic equation of dynamics, then we can actually say that gradient of P by rho will simply be counterbalanced by the effective gravitational potential. Now if you remember that effective gravitational potential actually includes the true gravitational potential and some equivalent potential which is coming out of the centrifugal term, right? So if this balance equation is still valid. Now of course when we have an incompressible fluid, then rho also enters into this gradient. So you have gradient of P by rho is equal to minus nabla or gradient of phi effective, okay. Now for compressible case we simply have this, that gradient P by rho, so rho is a variable, is equal to minus gradient of phi effective. And if we just take the curl on both sides, then we will simply obtain that curl of P cross curl of rho, there will be of course, as you know, that by some rho square term, okay, because if you take the curl on both sides, this will be 0 because this is a pure gradient term and this has a 0 curl. So basically this will act on this 1 by rho term and it will give you minus gradient of rho by rho square, and so the whole term's curl will simply be curl P cross curl rho by rho square, and that will be equal to 0. If you remember, this term is nothing but actually by rho square, nothing but the baroclinic term, okay. Now this one just says that the gradient of P and the gradient of rho, they are parallel. So it simply says that, as we know that the gradient direction is the normal to the direction of constant pressure and constant density, then we can say that the contours of constant P and constant rho are also either parallel or coinciding, right? It is simply like this. If you have a surface with constant P, then the gradient direction will be this, normal to the surface. Okay, locally normal. Again, here this will be in this direction, here this will be in this direction, local normals. Now if I simply say that the gradient direction for the rho is also in these directions, okay, then of course the possible contour for the constant rho will be something like that, either this or this one itself. So either those two will coincide or those two will be parallel, right? Now if they are parallel, okay, then actually you can say that from this equation it is true that this equation is always valid. So this one and this one, they will also have the same direction, because gradient of p vector and gradient of phi f vector, they are just connected by a rho, which is a scalar. We don't care whether this is a constant or a variable. Okay, even if it is a variable, these two vectors will be simply parallel. So that's why we say that this will also be parallel to the contours of constant phi effective, which are expected to be spheroidal shape, and that we actually saw in the last lecture, that the phi effective is expected to be of the spheroidal nature. Okay, so finally we have now three contours. One is contour for constant p, contour for constant rho, contour for constant phi effective, and all of them are either parallel or coinciding. Now if the ideal gas law is still valid here, which is completely a valid approximation here, because we are talking at moderately high temperature, where you can easily assume the gas to be ideal. Okay, then the contours of equal temperature are also coinciding and spheroidal. Okay, so that is true. Okay, so because then p will be proportional to n and t, and so gradient of p will simply be equal to n gradient of t plus t gradient of n. So if the n is nothing but the number density, so it will be something very similar to rho. So if this one and this one, they are parallel, this one must be parallel. So we have four type of contours which are either parallel or coinciding. Okay, so finally the conclusion is that for rotating stars, mostly when we are talking about the rotating axis to be vertically upward or something, right? Okay, so then what we get is an oblate type of spheroid. Like the spheroidal shapes can be of two types. One is called the prolate, where the vertical elongation and the horizontal contraction occurs, and one is called the oblate, where the vertical compression at the equatorial or the horizontal elongation occurs. Okay, so in our case, most of the cases we can see the oblate spheroid. Okay, and if it is oblate spheroid, so the rotating stars themselves are oblate spheroids, then we know that all the phi effective, the contours of equal phi effective, equal pressure, equal density, equal temperature are all oblate spheroids. And if they are oblate spheroids, then one thing is true, that the distance, okay, now you see, you try to understand that you try to imagine this whole spheroid to be consisting of some spheroid shells, okay, like this. Now it is true that if it is just a sphere, and can be thought of as a number of concentric spherical shells, then the distance between two successive shells are actually constant, independent of the azimuthal directions. But here what happens, the distance, so you see, like you have oblate like this, and you have something like this. So you see that the distance here is greater than the distance over here, but this is isothermal contours. So let's say here you have some sorry, let me just draw in a proper way. So yeah, this is something, yeah. Okay, now here the distance between two isothermal contours, they are decreasing. So now let's say here your temperature is T1 and here your T2. So T2 minus T1, the temperature gradient near the poles will be by some, will be T2 minus T1 divided by, sorry, T2 minus T1 divided by the distance between two contours near the pole, that is delta P, and the same thing, the temperature gradient near the equator will be delta equatorial. Now as delta equatorial is greater than delta P, then the temperature gradient will be greater in poles with respect to the gradient near the equator. Okay, and that is the gradient. So gradient simply means that dt dx type of thing. So dt is constant, but dx is now smaller. Dx is smaller near the poles. That's why dt dx is getting a larger value. Okay, so the gradient is higher. So since we know that if we are just talking, thinking of the radiative flux, okay, so we just think that due to this temperature gradient, some radiative flux is coming out. Then we can easily say that the radiative flux which is coming out due to this temperature gradient, okay, which is of hydrodynamic origin, because this temperature becomes due to the the ideal gas law, which is like a fluid type of thing. Okay, it should not be a fluid at so this is a, okay, so this is a hydrodynamic condition, P N kBT. Okay, so N is the number density, P is the pressure of the fluid, T is the temperature of the fluid, this type of thing. But so if delta gradient of T is greater, then the corresponding radiative flux we know from our radiation physics. Okay, physics of radiation, one can easily say that radiative flux is increases when gradient of T increases. Okay, not always proportional to gradient of T, but something, but this is actually increasing with gradient of T. So as gradient of T is greater near the poles than the equator, then the polar radiation flux is greater than the equatorial flux. Okay, but the only problem is that we all know that the energy which is radiated, okay, should come from the normal, so normal energy source of the star, and the normal energy source of the star is nothing but the nuclear reaction. Okay, but this nuclear reaction gives some radiative flux estimation which does not match with the hydrodynamic estimate of the radiative flux, and this was for the first time remarked or noticed by von Zeipel, and we call this as Zeipel paradox. Okay, so how to overcome this Zeipel paradox? Well, so then one has to take the existence of a meridional flow, okay, in the interior of the star into account, and actually that flow changes the hydrodynamic equation. Okay, and gives takes part in the force balance, and finally you will see that this will exactly give the matching with the nuclear the the estimated radiative flux which should come from the nuclear reactions. Okay, so this is known. So this meridional flow in the interior of the star is known as Eddington-Sweet circulation, because it was for the first time discovered by Eddington, and Sweet did the theory in 1915, 25 years later. Now, it is true that for most of the main sequence star, for example our Sun, the rotation is not very strong. Okay, it is true that till now we have seen that this rotation can give us something. So for example, from rotation of a compressible fluid we can see that the temperature, the different iso pressure, iso density, iso temperature, and iso gravitational effective potential contours are all actually parallel and either parallel or coinciding with the oblate spheres. Now coming back to the question is that and also from that we have estimated, okay, just modifying by this circulation, we have estimated the radiative flux which comes out both from different parts of a star. So the energetic part was okay, but the question was that whether and when when the effect of rotation can be important or cannot be important for a star. So then the question is that whether the dynamics. So we have seen that in this previous part we have already assumed that the rotational effect is there and the system has an oblate oblate spheroidal structure, everything that's okay. But coming back to the very fundamental question, now is it true that for all stars the effect of rotation is important at all? Well, the answer is tricky. So for most of the main sequence stars, for example Sun, the rotation is actually not very strong. Okay, and when we say the rotation is not very strong, what is the meaning for that? The meaning is that that quantitatively it is simply equivalent to saying centrifugal force is very small compared to the gravity force. Or actually in the phi effective, okay, in the phi effective we have two parts, one is phi, another is this centrifugal part. Okay, now this centrifugal part is negligibly small for the main sequence star. So phi effective is almost equal to phi. Okay. Now for this type of stars, actually there are models which totally neglect the effect of rotation, and we have simply reasonably good results for those stars. But it simply does not say that in astrophysics whenever you see stars you just forget about rotation. Why? Because one question is very crucial, that this was only for the main sequence stars, but what happens if we are considering a collapsing star which is at the somehow at the the so-called old age of its lifetime, it's not a main sequence star? Then what happens? Then this is very tricky and very interesting. Let's say for such a star which is collapsing under its self-gravity, okay, so the radius A, let's say, decreases from some current value, okay, And if radius A decreases, the moment of inertia decreases as well, okay, because moment of inertia goes as A square. So if radius A decreases, the moment of inertia also decreases as A square, okay. Then if the angular momentum is conserved, because we are just thinking that there is no external deforming torque or something, okay, so the angular momentum is conserved, the radius is decreased for some, internal mechanism, okay, for example self-gravity. So that is not causing any harm to the conservation of angular momentum. Then what happens? Then the angular speed simply, which is omega, it goes as A to the minus 2. And if A is decreasing, it is actually increasing, right? And then if this is increasing, this follows a law of A to the minus 2, then the centrifugal acceleration, which has a law of omega square A, will now follow A to the minus 4 times A to the minus 3, correct? So the centrifugal acceleration will also go up as A to the minus 3. Now, gravitational accelerations, so we see that when A decreases, centrifugal acceleration actually goes up at this. But gravitational acceleration increases, but it increases only as A to the minus 2. So centrifugal acceleration will increase much more quickly, much more rapidly, okay. So after some time, gravitational term will be simply dominated by the rotational term, that means the centrifugal term, okay. So now we just want to explore the whole thing just by us taking simple example, okay. So let's say the radius of a star like Sun is suddenly decreased from 10 to the 11 centimeter to 10 to the 6 centimeter. 10 to the 6 centimeter is a characteristic radius of a neutron star. Then actually one can calculate simply that the rotation period changes from a month to less than 10 to the minus 3 second. And if that happens, the centrifugal force is so strong with respect to the gravity force, then actually some matter cannot be bound by the gravitational force and some part of the material of the star actually flies off, okay, under the influence of centrifugal acceleration, okay. So it is exactly something very analogous that whenever, let's say, you have some, for example, you have some fluid bulb type of thing, and you just rotate this fluid bulb very fast. So after some time, let's say some fluid will be splashing around, right? That is because the centrifugal force is much more important than the gravitational force, which is trying to bind the the fluid particles on the surface of the bulb, okay. And that's why this will just coming, so the drops of the fluid drops will just come around, flies off the bulb surface and it comes out, okay. Now we will do some interesting thing as well. So we also talk, so first we talked how should the iso pressure, iso density, iso temperature contours look like. Then we talked about another aspect which is very interesting, that for the collapsing old stars, rotation for example the neutron stars, rotation actually is very important, so we cannot neglect it, unlike a main sequence star, okay. Now finally we will see something related to that. We should recall that the maximum, so when we treated the spheroidal structure, possible spheroidal structure under the interplay of self-gravity and rotation, we showed that the maximum limit of the rotation rate for a mass of incompressible fluid is given by omega square, which should be then less than 0.449 pi g rho. Okay, so if the rotation rate is greater than this value, this is this critical value, then some mass will fly off. And naturally from this one we have a lower bound for the time period, because the time period is 2 pi by omega. Okay, and we can say that the time period should also be greater than 2.05 into 10 to the 4 by root over rho. Of course the fluid is nearly incompressible here. Okay, now we know that neither for the white dwarf or the neutron stars the fluid is incompressible, but we are just doing some rough theory here. So for a typical white dwarf, the matter density is almost 10 to the 8 gram per centimeter cube, and this simply gives us a minimum time period, that means the lower interval, this one, to be almost equal to 2 seconds. But for neutron stars, where the density is much more greater, 10 to the power 14, 6 times greater, then the minimum time period permissible is 2 into 10 to the power minus 3 second. Okay, that is the time period, okay, below which if the star rotates, then the star will not sustain, okay, its structure because of the centrifugal force, which is largely then dominating over the gravitational attraction force. Okay, now in the year 1968, he for the first time discovered pulsar, and he saw that the period of the pulsars are the pulsating stars. Okay, so period was 1.377 second, and he immediately understood that this is somehow roughly less than this. Okay, so pulsars cannot be rotating white dwarfs, but they should be rotating neutron stars. One question that can come to your mind at this point, that we have already talked about stellar oscillations, and for that pulsation was also observed. So why for pulsars the pulsation was assigned not to the oscillation of the star or the stellar object, but to the rotation? That is simply because if you just analyze, taking the if you just calculate the eigen frequencies, okay, or the eigen modes of oscillation of a white dwarf or a neutron star, you will simply see that the corresponding frequencies do not at all match with this observed frequency. Okay, so that's why the only possibility was to confer that the pulsation was due to rotation. Now till date, this is very interesting, the fastest rotating pulsar is the so-called millisecond pulsar, with period of 1.558 into 10 to the power minus 3 centimeter, which was for the first time realized by Baker et al. In the year 1982. But this one, now you see, this has a period of 1.558 into 10 to the power minus 3. Now you can tell me that what is happening here. This is even less than this one. So neither this nor this. Well, this is not exactly the cause. This is not exactly not exactly a problem, because of the simple fact that these pulsars are rotating neutron stars, which are very massive and very compact. So this star material is fairly compressible, first of all, and due to being very massive and very compact, the general relativistic conditions, that means the curvature in the space-time due to that neutron star, should not be forgotten. So that these two things should be taken into account, and if you take into account, you will actually see that, so for white dwarf the general relativistic correction is not that important, but for neutron stars this is important, and you can actually see after inserting all this like modifications that the minimum T is well below this 1.55 into 8 into 10 to the power minus 3. So we are saved again. Okay. Now, but this is also like this is a very complex thing. So this is one of the possibility, of course, that the general relativistic condition and the compressibility can can be the original reason for this discrepancy. Okay, but this is true that we are not 100% sure of that. Now, just like an old collapsing star, rotation is actually important during the birth of the star as well. This is very interesting. Okay, and what happens? So previously we discussed about the formation of a star by Jeans instability and the corresponding fragmentation. So what happens that when the under Jeans instability, when the a star forming cloud is collapsing, thereby making the system much more prone to star formation, then suddenly if the rotation becomes important, because of the same reason we have just mentioned a few minutes ago, that the density, the radius is suddenly decreased, so the increase in the centrifugal force will be dominating the increase in the gravitational force. Then suddenly the effect of rotation simply becomes important to counterbalance and thereby halting the contraction or the collapse process. Okay, now the question is, finally we can see the stars. So what's happening? If every time this was the reason, then we could have not seen any single star till now. So one very plausible theory is that the magnetic stresses, they actually somehow mitigate in some sense the effect of the rotation. Okay, and this simply finally leads to the further collapse of the star forming cloud, thereby finally giving birth to a star. Okay, so you see that the astrophysical stories are interesting, but at every step we have non-trivial things and we have new effects to include in order to just explain the observed phenomena and observed things. Okay, so this is very important in the domain of astrophysics and the research in astrophysics, that we should be very open-minded. That means, you see, like this till now we have not talked about magnetic field. We are doing everything hydrodynamics, but we should not be closed so that we just say, well, while doing hydrodynamics we will not be looking at the magnetic field and the plasma aspect of the fluid. That is never working in astrophysics. Okay, you see that some inconsistency in this hydrodynamic model must be explained in the light of the magnetic stresses. Okay, so and due to all these things, basically in the next part I will switch to the very interesting domain called the domain of plasma, simply because not simply because this is explaining in some cases the possible phenomena, but in reality all the fluids in astrophysical framework are plasmas. Okay, sometimes the plasma is weakly ionized. That means there are many more neutral molecules rather than ions and electrons, but sometimes they are quite strongly ionized. Okay, just before ending this rotational part or this context, I would try to say one simple thing, that the rotational effects are extremely complicated in case of the galaxies. In case of the galaxies, the treatment just by using hydrodynamic fluid equation is not very easy. So then you can actually use like a collision moment equations, like a collisionless system. Okay, so you can see in the book, this is beyond the scope of the current course, but it is also true that as I already mentioned, that the ellipsoid type of structures which are already observed in case of in case of the so-called elliptic galaxies do not contain much angular momentum, and that's why this ellipsoid structure is really due to rotation. Well, we don't know. Okay, but on the other hand, this is true that in several cases you can actually see the effect of the rotation. Okay, the effect of the rotation in several, even in several spiral galaxies, sometimes give you an estimated radiated flux. Okay, which does not match to the observed radiated flux or radiated energy flux from that galaxy. Let's say from a spiral galaxy. Then sometimes the main reason not sometimes, but most often, the main reason is thought to be the presence of so-called dark matters. Okay, so this is all about to inspire you, or rather to give you an impetus towards the interesting domains of astrophysics. Okay, so from the next lecture we will start discussing plasma. Okay, thank you very much.